European algebra takes its origin from one single book written in Baghdad in the 9th century by a man called Al-Khwarizmi. That was his usual name. His real name was much longer. It began Mohammed ben Musa, etc., etc. But he was called Al-Khwarizmi because he came from Khwarezm. The title of his book was Al-Jabr wal-Muqabola, which means something like collecting and cancelling terms of an equation.
Al-Khwarizmi was the first in a long line of outstanding Arab mathematicians. He worked in the library of the Caliph al-Ma'mun in Baghdad, where many Greek manuscripts were translated. At about this time, the new capital of the Muslim Empire was being built at Samarra, and the minaret and the walls of the great mosque there still survive. Al-Khwarizmi's name lives on in our word algorithm, and his algebra, of course, became our word algebra. Al-Khwarizmi's algebra deals with various types of quadratic equations, always written out in words and always with positive numbers for coefficients. He correctly distinguished and solved three types of quadratic equation, which in our notation would appear as x squared plus ax equals b, which he called a square and roots equal to numbers, x squared plus b equals ax, which he called a square and numbers equal to roots, and ax plus b equals x squared, roots and numbers equal to a square. And there were three more, where a term is missing and the x squared term is multiplied by a constant.
The solution of these equations is, of course, just the same as the solution we learn at school, because there is only one correct solution. As a motivation of his calculations, he gives drawings. It's a large square with sides x plus a and x plus a. It's divided into two smaller squares and two equal rectangles. And this is the way he formulates and proves our equation x plus a squared equals x squared plus 2ax plus a squared. The study of algebra in Europe really begins with a translation into Latin of Al-Khwarizmi's book on algebra, made by Robert of Chester in 1145. Somewhat later, the Italian painters became interested in perspective. They were very fond of it. They studied it and used it in their paintings. But the new ideas in algebra came only later, not before 1500. The knowledge in algebra of the Middle Ages was summarized in two books at the end of the 15th century. One of these books was written by Nicolas Chuquet in 1484, and the other about the same time by the friar Luca Pacioli, who was in the service of the Duke of Urbino. Urbino is a small town in the mountains not very far from Florence. The title of Luca Pacioli's book was Summa de Aritmetica Geometrica Proporzioni e Proporzionalità. The book was written in Italian, not in Latin, and printed 1494. The word he used for the unknown was cosa, which means thing, the unknown thing. So he would write, yes, he would write the quadratic equation, for instance, as the square and the thing are together equal to 6. What is the thing? Just as Al-Khwarizmi did, he distinguished 3 cases of mixed quadratic equations, just the same types as Al-Khwarizmi, and in addition to that, he distinguished 3 more cases in which one of the 3 terms was missing. So there were 6 cases in all, and he gave explicit rules for solving all the 6 cases. Pacioli also considered cubic equations, but in his opinion, no algebraic treatment of cubic equations was possible. He said it was, in his opinion, as impossible as squaring the circle. Only 10 or 20 years after this was written, Scipione dal Ferro, a professor of mathematics at the University of Bologna, succeeded in solving an equation of the type x cubed plus ax equals b. Or, in his terminology, the cosa and the cube are equal to a number. You see, he took one of Al-Khwarizmi's types of equation, the square and the cosa equal to a number, and he replaced the square by a cube. He succeeded in solving this equation by making a substitution, x equal to u minus v, where u and v are new unknowns. We shall discuss this solution later on. Scipione kept his method strictly secret. He revealed it only to his pupil Antonio Maria Fiore. Why did he keep it secret? Well, at this time, public contests, often for considerable sums of money, were a normal form of competition in the learned world. You see, university appointments were mostly temporary and had to be renewed. The decisions of the Senate were strongly influenced by the outcome of these contests. So anyone who was in possession of a secret and powerful method for solving a certain kind of problems had a great advantage over his competitors.
These were troubled times for Italy. Charles V had been elected Holy Roman Emperor in 1519. Italy at that time was a collection of smaller states, and the territories that made up Charles's empire were scattered. He ruled over Sardinia and Sicily and Naples, Milan, and the lands to the northeast of the Adriatic and to the north and west of Italy. He faced many difficulties: Lutheranism, the challenge from France, and the increasing power of the Turks under Suleiman the Great. War was the keynote of his reign, and it added to the problems of ordinary people, already troubled by disease and want. The Italian universities were in a state of disarray. Salaries were often not paid, and sometimes the universities had to shut down. There was a decisive battle between Charles V and the French at Pavia in 1525. With the help of Spanish and German mercenaries, the French were routed by the armies of Charles, and Francis I, the King of France, was taken prisoner. The battle effectively closed the university, and many of its students went off to Padua, one of the leading scientific universities of the time, which was under the protection of Venice and so comparatively peaceful. War again closed the university at Pavia in 1542, and this time the entire medical faculty went to Milan, which was a centre of medical scholarship. At Bologna, where Charles V had been crowned by the Pope in 1530, there was one of the oldest universities in Europe. It was a major centre for mathematical studies, and Scipione was professor there.
After the death of Scipione dal Ferro in 1526, Fiore felt free to exploit the secret he knew, the solution of the cubic equation. He challenged Tartaglia to a public contest. Tartaglia was a teacher of mathematics in Venice. He had written several books on mathematics, and he was most successful in taking part of public disputes and contests. The contest of Tartaglia and Fiore was scheduled to take place in February 1535. The conditions were: every one of the two would write 30 questions about 2 months beforehand, so that the other one had 2 months' time to think of the solution. The loser would have to pay 30 dinner invitations to the winner and his friends. Tartaglia had prepared a variety of problems from different parts of mathematics, but Fiore had only one arrow to his bow. All his problems were of the type the cube and the cosa. Tartaglia came into great difficulties because he didn't know the secret of the solution. He thought very hard, and in one sleepless night, he himself gives the date. It was the night from the 12th to the 13th of February, 1535. Only 10 days before the deadline of the contest, he rediscovered the solution. The inspiration came over him. And then he was able, in a few days, to solve all the problems the other one had written. And the other one, Fiore, was said to be strong in calculation but weak in theory. He could not solve most of Tartaglia's problem, and he was declared the loser. At this time, a new and powerful figure enters the stage, Girolamo Cardano. He was not only a great mathematician, but also a famous physician, an author of popular philosophical books, an astrologer, and also a passionate gambler. He wrote a book on probability, the first book ever written on probability and on gambling. Because he was not admitted to the College of Physicians, he wrote a book on the bad practices of medicine, which embarrassed the other practitioners of Milano very much. The book became so popular that they were finally forced to admit him to the college. He became so famous as a physician that the Archbishop of Scotland, John Hamilton, at the time of Mary, Queen of Scotland, asked him to come to Scotland because he was suffering very much from illness. He came and he cured the Archbishop. Cardano heard of the contest between Fiore and Tartaglia and about the solution of the cubic equation. He tried very hard to get the secret out of Tartaglia, but he didn't succeed. And then he invited Tartaglia to come to Milano and to dwell in his house, and he promised him to introduce him to the Marchese del Vasto, the Spanish governor in Milano. Tartaglia was very much interested in that recommendation because he had made some inventions in artillery and wanted very much to tell the Marchese about these inventions. So he invited the invitation, and then Cardano finally succeeded in persuading him to tell the subject, but Cardano had to swear an oath never to publish these inventions. The text goes thus: I swear to you by the sacred gospel and on my faith as a gentleman, never to publish your discoveries if you tell them to me.
Tartaglia conveyed his secret in some lines of verse. The first 9 lines deal with the equation x cubed plus ax equals b, and the following 9 lines with x cubed equals ax plus b. Let's look at an example. Suppose we have x cubed equals 6x plus 6. Now we're to look for a solution of the form x equal to u plus v, where u and v are new unknowns. Substituting, we get u plus v, or cubed, is equal to 6 times u plus v plus 6. The method then reduces this one equation to 2. U cubed plus V cubed equals 6, and U cubed times V cubed equals 8. Now these two simultaneous equations involve the two unknowns U cubed and V cubed, and simultaneous equations in this kind of form had been known since Babylonian times. The solution in this case is U cubed equal to 4 and V cubed equal to 2, so that x equals U plus V is equal to the cube root of 4 plus the cube root of 2. But just how can the cubic equation in U plus V be reduced? Well, starting from U plus V, or cubed, equal to 6 times U plus V plus 6, we expand the left-hand side to get U cubed plus V cubed plus 3uv times U plus V equal to 6 times U plus V plus 6. Now, if only we can remove the two terms next to the equality sign, we'll have one simple equation. U cubed plus V cubed equals 6. And we can do this if 3uv times U plus V is equal to 6 times U plus V, or cancelling out, if 3uv equals 6. That is, uv equals 2, or U cubed V cubed equals 8. And so we get the two equations we want, and the solutions for U and V, and hence for x.
In 1536, a boy of 14 years old, Lodovico Ferrari, from Bologna, came to Cardano and was employed as his secretary. He helped Cardano to write a book called Arithmetica. He learned about the solution of the cubic equation, and Cardano asked him to try to solve biquadratic equations. That is, equations in which a term x to the 4th occurs, in addition to the other terms we know already. Ferrari succeeded in solving this equation. He developed a general method to solve all biquadratic equations. When he found this, he was not even 20 years old. He was an extraordinarily gifted young man. By now, the master and the pupil, Cardano and Ferrari, had accumulated a vast amount of new and important material. And of course they wanted to publish it, but they were in great difficulty because of the oath. Cardano wanted to write a book, his main work on algebra, called Ars Magna, but he couldn't publish it because it all depended on the solution of the cubic equation, which he was not allowed to publish. Now they heard that the first invention was not at all due to Tartaglia, but to Scipione dal Ferro. They traveled to Bologna and they looked into the papers of the deceased Scipione, and there they found the solution. And now Cardano felt free to break his oath and to publish the whole thing in the Ars Magna. He said quite clearly who had discovered what. But still, Tartaglia was furious, and a long discussion in pamphlets between Ferrari and Tartaglia followed.
Renaissance algebra, which began in northern Italy, was greatly stimulated by the publication of the Ars Magna, and it was to remain the most important work in algebra for almost 100 years. Modestly, Cardin lists it without comment in his autobiography when he records the 131 books he wrote during his lifetime. When he died in Rome at the age of 74, he had survived Tartaglia by 19 years and his friend Ludovico Ferrari by 10.